Hey guys, welcome to Entagma. It's summer in Germany. It's daring hot. Both of us have not slept, but that's no problem. Got Niklas Rosenstein with me, our Python guy. So that's an indication that today we are going to script a bit. Today's tutorial is about something totally different. It's about the workflow from Illustrator into Houdini and from Houdini back into Illustrator. And while getting stuff from Illustrator into Houdini is relatively straightforward, getting it back from Houdini into Illustrator. That's why Niklas is here. And when Niklas is here, you know it's about scripting.
Yeah, so we're going to do an export for the paths as SVG.
Cool.
Because if we do that, we're going to get actually complete paths in Illustrator. Because with the DXF export in Houdini, you just get cluttered paths, and it's not really good to work with them. So
cool. So let's get started.
Okay, to get artwork from Illustrator into Houdini, this is what I usually do. I just create a file. In most cases, I make it square, just some random dimensions. I usually go with 15 by 15 centimeters, but whatever works for you. You can still scale it later in Houdini. So create that artwork, and in my case, I'm just going to post some shape here. That's just a character out of Wingdings 2, I think, or Webdings, that I converted to an outline. And I'd like to bring this artwork over to Houdini. So let's save this out, and in my case, I need to save this as, let's call it Wingdings 3. And I know I'm on an ancient version of Illustrator here, but this should work with newer versions as well, because it's not about how new your Illustrator version is, but how old you can save the file. And what I found was most reliable is save it as Illustrator 8 file. So let's do that. Gives me a warning that not all features are supported in an older file format, so let's accept that. And then head over to Houdini. So in Houdini, I'm going to drop down a file node, which is just your standard geometry node, including the file loader here. And I'll select my Illustrator file that I just saved out. Remember, if you have incrementally numbered files, Houdini tries to import them as a sequence, so let's uncheck Show Sequence as one entry, and select our Wingdings3.ai here. So that's the file that comes into Houdini, and we see some issues with that here. So first, it's off-center. So let's fix that by dropping down a transform, wiring it up, and scrolling down here, check Move Centroid to Origin. And of course, let's wire this up again, highlight it, and again, click Move Centroid to Origin. So that only works if you've got geometry wired in here. Then that centers the geometry. Let's add a color to it. So it's not black anymore, but color it white instead. And let's fix that filled hole here. The way to do that is just using the hole swap and wiring this up in here. And this looks a bit weird sometimes because it tries to bridge those holes. You can also check unbridge holes if you don't like that. However, then Houdini assumes that the inner polygon is filled. Also, what you'd like to do sometimes, so let's highlight the point display here. So this is really irregular. So this is brought into Houdini as a NURBS or a Bezier curve. So let's convert this using a convert node to a polygon. That's the default setup. Let's wire this up and highlight it. And what I'd like to do is I'd like to dial up the level of detail in U and V to 1. So we get as detailed of a geometry as possible. So this is how I bring in closed shapes into Houdini. And I stumbled upon this one problem where I just had a spline. So let's just create a test object here in Houdini using the pen and marvel at my amazing Illustrator skills. And let's just save out this one line as test line 01. Again, Illustrator 8. Ignore the warning and go back to Houdini. And load that using another file. Select the test line and highlight it. You can see, in addition to all of the shenanigans like the transformation, Houdini displays this line as a closed polygon. And luckily some guys on the Houdini forum pointed me towards the right direction. So what you need to do is, on one hand, again, convert this into a polygon. And on the other hand, use the ends SOP to open these curves here. Like this, and now I'm back to my beautiful hand-drawn Illustrator curve. But back to the imported polygeometry from beforehand. So let's extrude that using the poly extrude, wiring this in here, then increasing the distance to just give this some depth, and then throw this into a VDB using the VDB from Polygon, which will create a volumetric representation of that surface. Let's increase the resolution by decreasing the voxel size, and you already see issues here. That stems from the poly extrude, where I forgot to check that we want the back face as well. So let's scroll down here and check output back. So that closes this, and then on the VDB from polygons, this is what I get. There are some issues down here, which I will ignore for now, because what I have in mind with this, let's still decrease the voxel size a bit. What I have in mind for this is to smooth it out using the Smooth SDF node. Wire this in, highlight it, maybe set it to Gaussian blur like this, and maybe increase the filter voxel radius so this blurs out even more, like so, or maybe even set it to 3. Yeah, I like that a lot. So we smoothed the whole shape now, as if it was made from some soft material that just melted away. Let's convert that back to a polygon using the Convert VDB. We want to convert it to polygons, and we wire it in here, highlight it like that. So now this should be our starting shape for the actual setup that we're going to build. And what I want is I want to generate geometry that resembles those isocontours. So what I'll first do is I will generate those section lines. And while there are multiple methods for doing this, the one that I find easiest, albeit a bit slower than some of the other methods, is using a boolean. So we'll pipe in this shape on the one end, and on the other we need something to intersect this in regular intervals. So I will drop down a grid first and use this grid here. Just maybe scale it down a bit to say 3 by 3 or maybe even 2 by 2. That's enough. And also give it only 2 rows, 2 columns, so we end up with one polygon here like this. Next I'll just use the standard old school copy and transform to just copy this while offsetting it to maybe say 0.01. Yeah, and let's make 100 copies of that, and also move the original grid down along the y-axis. So all those grids intersect my geometry. Let's wire this into my boolean too, highlight the boolean, and in here choose operation seam. So that will detect the seams of the intersection here. Let's drop down a null, call this one out_boolean, and wire our boolean in here. Wait a bit. The boolean takes some time to process the geometry, and then when we hide our copied grids here, we can see this is the resulting geometry from that operation. Okay, most of us have seen that. I like the looks nevertheless. Okay, let's disable the grid for now. Now, what bugs me when I look at this is that I can see through the whole geometry, so lines on the backside of my geometry will appear even although they are on the backside of the geo. And the admittedly a bit funny and a bit nerdish way of dealing with that goes a bit like this. So what I want to do is hidden surface determination. So when you look at this here, this should be a cross-section of our scene just with some example geometry here. And this is our camera, and this is our camera's view frustum, so what the camera sees in the scene. We'd like to find out which parts of the geometry are visible to our camera. So, which sides? Is this side visible to the camera? Clearly yes. Is this side visible to the camera? Clearly no. But how do we go about finding out about this? Let's build a quick algorithm. In our case, the geometry will consist out of uniformly subdivided lines, so we'll have points spaced evenly along those lines. And let's use that to our advantage. What we're going to do is, for each point, we will send out a ray pointing towards the center of a camera. And we will check if this ray intersects any geometry on this way. And if it doesn't, the point from which the ray hits the camera is visible to the camera. So, for example, a ray from this point to the camera does not intersect anything, so the point is visible. However, this ray, starting at this point towards the camera, intersects geometry here. So this point here is not visible to the camera, and we can delete it. And the same goes for all of these points, for example. So this point, on its way to the camera, intersects the geometry here. This point even intersects the geometry twice, once here and a second time here. And so does this point, having the first intersection here and the second one here. So what we need to do is for each of our points, we will send out a ray to the camera and check if that ray intersects any geometry, and if it does, we just delete the original point. And I'm very open to any suggestions of more intelligent, faster, easier to implement algorithms than this. It's just, I had fun implementing this. It's just a few lines of vex, and I really enjoyed it, so let's do it. So what I'll need are these points here from the lines, and just to be sure, let's drop down a resample here to uniformly resample those lines, and the point distance here, that's a bit coarse, so let's dial down the length to 0.005, like so. So those points are now evenly spaced apart. And also to be able to just delete points out of that line and to have the respective line segments disappear too, let's use a cheap hack and drop down the convert line, which will convert these continuous lines into individual segments. So each one of those tiny segments here now is an individual line. And that enables me to just delete one point and the line segment will disappear as well. So let's disable the point display again. And what I need too is some geometry to intersect all those points with. And I'm going to use this geometry here. However, I still need a camera. So I need to know where to shoot my rays from those individual points. So let's drop down a camera by control-click on the camera symbol, which just drops down a camera in the position that my viewport camera was in. And let's just lock this camera so it tumbles with me when I tumble in the viewport. So that moves the camera, maybe like this. So what I'd like to have in here now is a point that tells me where the origin of my camera is in the scene. And I can get that using an object merge, which will merge parts of our camera geometry into our current object network here. So I'll just select my camera here and just select the cam origin. And I want to transform this into this object. So let's unlock the camera here and zoom out a bit and maybe highlight the object merge here. And I can see this point appeared here, this one here, which is the origin of our camera, and that's where we shoot the rays to. Okay. So we've got the geometry for intersection, we've got the lines that we want to check, the points that we want to check, and we've got the position of our camera here. Let's drop down a point wrangle, and we want to work on these lines here, on the points of these lines here. We want to check against this geometry, and we want to use the camera position here. So 3 of my ports wired up. Wow. And to determine the intersections, I want to use a vex function called intersect_all. Let's just go to the help menu here by hitting F1. And there are 2 intersection functions. And there is another function that determines the intersection. It's called intersect. However, I like to use intersect_all because it allows me to dial in the precision of my intersection here using these parameters. It's a bit more elaborate to use, but in most cases it is crucial to be able to dial in the tolerance for intersection detection. So this one needs a geometry. That's just the geometry slot we want to check against. It optionally needs a group or allows for a group. So if you have a group of primitives against which you want to check intersections, you can put it in there. It needs the origin of our ray and the direction of the ray. And then it outputs 3 arrays, storing the intersection position, the intersection primitive number, and the intersection UVW coordinate. And these ampersand symbols in vex help mean that this function will modify these variables here and just store something in them. So we need to create those variables first, pos, prim, and UVW. Let's do that. Let's create a vector, call it IPOS for intersection position, and it should be an array. Same goes for the UVW, should be an array too. And finally, let's create an integer array, call it iprims for intersection prims, an array as well. So now, what we want to do is, we want to intersect our points with the geometry coming in through our slot with the ID 1. That's the second slot here. We don't have a group. We have the origin of our array, which is our current points position. Now we need the direction. We don't have that yet. So let's get it. The first thing we need to do is calculate the rate direction from our current points position and the camera position here. So let's get the camera position first. Creating a vector, call it campos. And it should be equal to, let's middle mouse on this object here. It's just 1 point, which stores the position of the camera. So should be equal to what's stored on our point coming in through our third input slot. That's the input slot with the number 2. The attribute we want to look up is P for position. And it's the first and only point with the point number 0, like this. So now that we have that, let's calculate the direction. Let's call it dir for direction, and it's equal to the camera position minus our current point position, like this. Now we have a directional vector. Let's store the results in our arrays IPOS, IPrims, and IUVW. And finally dial in the tolerance. So the first value tells me how precise the intersection analysis should be. And the second value tells me if it should merge intersections that occur within a given radius. And by setting this to -1, I don't want to merge intersections. So let's highlight this, and okay, no errors so far. That's good. Apart from all this information, we also want to know how many intersections we found. So that's what the function originally returned, so let's just store that into an integer. Let's just call it num_i for number of intersections. Now that we have that, let's check if our number of intersections is bigger than 0. So if we found anything, and if so, let's just remove our current point. Like this. And we see this somehow didn't work. This somehow yields weird results. Let's circle around it a bit. And while it reliably removes the non-visible parts of our lines on the back here, it kind of dithers the lines on the front. So why is that? Well, this is because of precision errors. What happens on those front-facing points here is they still intersect with the grid because they are exactly on this grid. So let's fix that by, instead of shooting the intersection ray from the points position, just offsetting that position slightly. So to the point position, let's add the direction and just multiply it with something quite small like this. And now that we offset the position, we can see we get correct results. So we just basically moved the point from which we shot the rays a bit away from the surface in order to not get those erroneous intersections. Let's look at it through our camera. We can see that's looking pretty neat. So we see we get some errors here and there. We can dial this in by adjusting this multiplier here. Also, what we could do is, after we converted our VDB, we could drop in a peak. So that'll just move the surface along its surface normal, which is something like this here. And we could just make it a tiny bit smaller, like this, and can use the peak to dial in the looks of our intersection analysis as well. So that generates the image that we want to output back to Illustrator. However, again, when I hover this, I can see these points are still three-dimensional. And what I need in order to output line drawing to Illustrator is have all my points lie on an XY plane. So we'll just have to output the X and Y coordinate and Illustrator will read that in. So what I could do is just feel tempted to just set every Z coordinate in here to 0. And I mean, let's just try that. And just multiply our current coordinate with 1 along the x, 1 along the y, and 0 along the z-axis, like this. So we just get this plane here, but you see the whole effect is gone. That is because what we're doing by just multiplying our position with this here, setting the z-coordinate to 0, is we just project those lines along the z-axis, so we don't get all this perspective madness from this camera here. So how can we make sure the perspective matches? Well, again, this is a slightly hackish way, and if you have suggestions on how to do this better, faster, more elegant, please let us know, please let me know. I'm happy for suggestions there. But what I do, or what I did, is I go up and create a grid, dive in there, set the grid to have 2 by 2 columns and rows, and set its orientation along the XY plane. And then go up again and wire this grid in underneath the camera, like this. And then just move this grid behind our geometry here. So let's say to -5 in our case. Again, let's look through the camera. So the grid fills the whole screen. So I could even move this back further just to be sure, like this, -12. So again, let's just view at the scene from another angle, like so. And what I want to do now is add a third geometry, dive in there, and again, merge a few things. I'll merge 2 objects here. On the one hand, let's go up again. I will merge my line art that I created here. So let's make this clean and add a null. Call this one out_line_art, like this. Wired up, highlighted. So this is just a null, which will result in my line art here. Okay, head up again, and in my geo here, I will import this line art here, out line art. So there it is. On the other hand, I will import this plane here, this grid, by just selecting our grid here, and just selecting this grid, highlighting it. And you can see it jumps now. That is because, again, I have to transform it into this object so it remains in its original position, like so. And now what I'm simply going to do is use the ray and project those points onto this plane here by using an attribute that I have to create first. So again, let's go up to the node where we generated our line art here. And in our point wrangle, we already calculated the direction towards the camera. And to project those points here back to the plane, which is just the opposite direction of the camera, let's just use the directional vector and just invert it. So let's just create another vector called dir, and it's equal to dir times -1, like this. So again, when I middle mouse over the out, I now have a directional vector on our points. Super. Let's go back to where we project those. And in the directional attribute, let's not use n, but dir, like this. And now we can see we have this geometry here projected back onto the plane. One step further, however, this plane is somewhere in space, so how do we transform it back? Well, let's drop down a transform sub for that. And what we want is to have this plane back in its original position. That means sitting with its center at 0, 0, 0, and oriented along the XY plane. So within the transform sub here, what I'm going to do is I go up again and highlight the camera, because the grid inherits the transform from the camera. So I'll copy, translate by right-clicking and copy parameter, go back into our, and let's call this project back, and this one generate lines. So I'll go back into our back projection here. And within this final transform sub here, I'll right-click on Translate and then click on Paste Relative References. So this will reference the translation of my camera. And again, do the same thing for the rotation. Copy parameter, dive into the project back, transform, right-click, and paste the relative references. However, this is definitely not on the center here. That is because I'm again applying the same translations that my camera already has. But what I instead want is I want to invert those. So now it's at least sitting axis aligned here. However, it's not sitting on the center point. Why is that? Well, when I go up again and highlight the grid, after I transform this onto the position of my camera, I set it back minus 12 units along the z-axis. And I have to account for that as well. So again, right-click, copy parameter on the translate of the grid, go back into the back project and add a second transform, wire this in, and in here, right-click on the translate, paste relative reference, and then invert the transformation again. And now when I highlight the last transform, I can see I have my camera image projected back onto an XY plane that's centered on the origin 0, 0, 0. That's exactly what I want. So how would I go about exporting this back to Illustrator? Well, I already mentioned there are several ways of doing this, and the most straightforward, most stupid way to do this is to use a DXF. So I just right-click on this node here, go to Save Geometry, then select the folder here and just maybe call this Isocontour_01, and then just append a DXF to it. Accept this, hit accept again, and then in Adobe Illustrator, let's just select this file here in the open dialog, hit OK, and there we have our artwork. So what's the problem with this? Well, you will see as soon as I try to select one of those isocontours. You see, they are all individual lines like these, which is not really what I want. So back in Houdini, what could I do? Let's just disable the back projection and again highlight our camera here, select that one, and go into the node where we generate the lines. So what we have here is this convert line, and this convert line is the cause that instead of continuous polylines, we have just individual line segments here. So let's merge them again using the polypath, just slam that in here, and when I middle mouse on the pointer angle, I see I have 22,000 primitives, and after the polypath, I now have only 187. So that merged those. Okay, let's go back to our back projection here. Again, this is what we write out to Illustrator. So let's try writing out that by right-clicking and again say geometry. Let's call it isocontour02.dxf. And let's try opening this in Illustrator. And you can see this doesn't work because for some reason, and this might be totally due to my ancient version of Illustrator, it's expected that the DXF comes in a different format or saves individual line segments. I'm not sure. I couldn't get this fixed. Again, if anyone has input, please let me know. So between this solution, which clearly doesn't work, and this solution here, which has unnecessary line counts here, because I want to be able to select individual lines and not individual line segments now, I thought, it'd be neat to be able to write out those vector graphics as an SVG, as a scalable vector graphics, which is kind of the lingua franca of vector graphics. So there are lots of tools out there who read SVG, who create SVG, and also browsers display it. Sadly, Houdini hasn't got an SVG export yet. So I called Niklas to the rescue.
All right, the first thing we need is a Python subnode. And we will need some parameters. So, for example, an integer parameter that defines the maximum size of our SVG image file. We'll use it to specify the size of the SVG based on the longest axis of our input geometry. So this is wider than it is high. So it's going to be like if the max size is 500, for example, it's going to be 500 pixels wide, and then based on the size ratio, it's going to have a height of like 400 or something in this case. And let's also add a file parameter for the output file name. All right. Now in our Python subnode, we can read these parameters using the eval_parm function from the node. So we'll just use eval_parm file name. Max size eval_parm. Let's check if we get the values that we expect, just with the print function, with the print statement. Actually. And you don't actually need these parentheses. I'm used to Python 3. That's why I often write these parentheses in a print statement. And if we activate it, we can see nothing and 500. That's because our file name is empty. If we choose something like the desktop, out SVG, for example, you can see that we get the correct path and the 500 that we we set here. All right, give it to 500 here. We can remove that again. And the next step would be writing to the file. So we're going to open the file in write mode with the quote W string. And let's say hello world, just to see if everything works as we expect. If we go to open the file, actually I've already got it opened here. You can see that it contains this hello world. So just to illustrate it more properly, let's just make sure it gets written again. Yeah, there you go, hello world. Now, SVG file is basically an XML file. So we'll need some kind of XML declaration, and I myself don't know this from the top of my head, so we'll have to just look it up in Google. Let's check Google. I'll just search for the SVG document structure. There is a document from the W3 organization here that contains the full SVG specification. This is actually what we need. Here's the XML declaration, some doc type with DTD schema, and the SVG root node, which ends here. And here's where we're gonna place our path elements for every polyline in the geometry. So let's copy this part first and write it to the file so that we actually have a valid XML file. I'll also add new lines at the end of every write, so you can actually look at the file more easily, because if there's no new lines, you'll just have one big chunk of text that you can't really check if for any errors from your eyes. So let's also add the closing SVG element, so we actually get a proper complete SVG file here. Activate the Python node again, so it will actually write to the file. And now if we go to Notepad++ again, reload, and you can see that we have a valid SVG file. If we open that up in Chrome, we should see nothing, which is pretty good, because if we had an error in our SVG file, it will actually tell us. So if we, for example, add a node that is not actually an SVG node here and not even give it a closing tag and reload the file, you can see that we have some error here. That's a good way to check if your file is properly formatted, because I'm not actually sure if Illustrator would validate your file in that way. So a browser will do that usually, except I think for Internet Explorer. So if you have that, go get something else. The next thing that we're going to do is determine the proper width and height of our SVG image, which is specified with these properties. And for that, we're going to read the maximum, like the size of our input geometry. So we're just going to read the bounding box of our input geometry with the bounding box method. And then we can get the size of our bounding box using the sizeVec function. And we will also need the lower left corner of our bounding box. So that's where we use the minVec function. Now we can just give this a print to see what we get here. Our size is not like 000 for now, because we didn't actually connect the geometry to our Python sub. Now we get something else, which is like, should be around the dimension for the structure. Now, as we said before, we want the longest side of our input geometry to represent the max size in the SVG. So if the x-axis of the size vector is bigger than the y-axis, we want the width to be equal to the max size. And now we want to calculate the height from the ratio of the height and the width of our input geometry. So we're going to use max size times size y divided by size x. And otherwise we'll just do it the other way around. So height equals to max size and width equals to max size times size x divided by size y. Let's give that a print as well. Actually, I'm going to need to open this in a separate editor. Just apply, and we can see that my estimate of 400 was pretty good actually. So we get 500 in the x-axis of our SVG file, which is the max size that we specified here, and 407 in the height of our SVG file, so that we actually keep its aspect ratio. Now we're going to substitute these values in our SVG, like where we write these. So we can use Python format strings for that. We'll just use these curly braces as placeholders. And we can, like, if you just don't add any unit, it's pixels. We could also just explicitly say it's pixels instead of centimeters, for example. And then we just call the format method and pass the width and height. If we apply, again checking in the Notepad++, reload, we can see that we actually have our values in the file as we expected. Next up is writing all the paths for every polyline to the SVG file. For that, we're gonna need to check how we actually need to write paths in SVG, what the format is. So again, we're gonna use Google to search for SVG path element. We can find something by W3 schools. So there's this SVG path element. It has a data attribute, and this data attribute is basically a string which consists of these characters and arguments for these characters. So for example, the move to command expects 2 numbers as argument, which is like the position where the cursor goes to. And then if you use line2 as the next element, it also expects 2 coordinates, or like a coordinate where it draws a line to from the previously moved to position. So here's an example that says path d equals, which is the data attribute. And it says it moves to the position 150, 0, and then it draws a line to 75, 200, and it then draws a line to 225 and 200. And then z just closes the path, as we see here. And that's what you get, this triangle. So that's basically all we need to do. Move and line2. For every polyline, we're going to create a path like this. Use a move command for the first point, then use line2 commands for every consecutive point. And then we don't actually want to close the path unless the polyline is closed. So going back to Houdini, let's actually create a function for that so our code becomes less cluttered. Write path, and it's going to expect a number of points. And obviously the file that we're going to write to. Let's do that as a first argument. And we can do fp write path d equals close new line data. And then we're going to need to produce the data, which we'll say is a string for now. And then for the first point, actually, if we don't have any points, like there could be an empty polyline, we're just not gonna do anything. Then for the first point, we need to write an m for the move to command, and then we want to write the coordinates of the first point. Let's keep a space in the end, so the next thing we add to the data will have a space between the 2 elements. Now for every other point, we want to write a line2 command. So we're basically going to do the same thing, just with an L instead. And that's our data, basically. Next up is that we iterate over every primitive in the geometry using the iterprims function. And we only want to look at primitives that are polygons, because polylines to Houdini are also polygons. So if the type of the primitive is not the same as the prim type polygon, we're just going to skip over this. Now to get the points of the polygon, or the polyline, we can use its vertices function, and then for every vertex we're going to read its point, and from the point we read its position, and this can be neatly expressed as a single line using list comprehensions. Use v point position for v in prim vertices. Now, just to see if we get anything useful or if that's what we expect, we can print the points. However, I would not recommend doing it just like this, because if you have a lot of geometry, the Houdini console is pretty slow, and like printing in general, and you will wait forever and you can interrupt this operation. So let's just introduce a break here so that we only get one print, and then we can see if that's what we want. So let's hit apply, and we can see that we've got a list of vector 3 objects here, which are actually just the point positions of the first polyline in the object. Next up is transforming these points so they actually fit in our SVG image space that we defined here. So let's introduce a function that we call transform points. And for every point, we will subtract the min vector from the bounding box and then divide it by size, and we get proper values between 0 and 1, and then we can scale them up with the width and height. Let's say p equals a who vector 3. Well, like we can use a vector 2 because we're just going to disregard the z value anyway. And let's say x is equal to px minus the min vector x. Then we're going to divide that by the scale x. And then we want to multiply it by our width. Basically the same applies to the y component. Subtract the min vector, the y component, and then we divide by the y scale, and then we multiply by the height. And what I just noticed now, it's not scale, it's size. We used variable size up here for the size vector. And then we've got our point, and then we can just yield it from the function. And then we can use, when we transform that back to a list using the list function. Let's see what we get. Apply, and we should see something in the console. Right, we actually get bigger values now. Now if you check our SVG file again, we got nothing because we didn't use the write pass function yet. So let's use the write pass function, pass our file pointer, and the points list. Hit apply, a misspelling maybe, yeah, it's not write path, so it's write path. Apply, check the SVG file, you see that we actually have a path element here with a data element. All these values look pretty good. Let's check in Google Chrome, hit reload, and we can see that we actually have, like, this looks very close to what we have here, or here. So that's probably the first path element. As you may notice, this path is completely filled. We actually want this path to just have an outline. And let's check the SVG path example again. We can see that down here they're actually producing lines instead of filled paths. And we can see that they're using stroke attribute and stroke width and set the fill to none. So that's just what we're going to use. We could just apply this here to see if it works the way we want. So let's just say stroke equals black, for example, and fill equals none. Save this, reload the file, and we can see that it's still filled because now we go. Misspelled that. All right, that looks pretty good. There's also the stroke width parameter. For example, let's say 3 pixels. We could add that as an attribute to the Python sub, but we're going to do that later on. Now let's head back into Houdini and do in the write path function, we will say stroke equals black and the fill equals none. And now we're going to remove the break and the print, which is also very important because, as I said earlier, it's going to take a while to print all these points to the console. Hit apply. Check the file. We can see that we've got a lot of paths here. Let's go to Chrome and reload, and you can see that we've got our geometry. The only thing is that it's flipped. So that's because in SVG, the y-axis actually extends downwards, whereas in Houdini, the y-axis extends upwards. So we can just mirror the y-axis. So we're just going to do 0.1 minus. Let's apply again, hit reload. And there we go. We can see some errors here in the SVG file, specifically here and around here. There must be something wrong in the code, so let's have another look. Oh, here I'm actually using the second point for the y-coordinate, which is obviously wrong. We also have to use the first point's y-coordinate as well. So let's apply again, check the file, and that looks way better. Now let's also add the stroke width parameter to our Python sub. Go again to the parameter interface and choose a float parameter. And say stroke width. And let's say maybe a default value of 1. And now we're going to read the value here. And in the write path function, we will just add the stroke width property. Say it's in pixels and pass the stroke width from above here. Hit apply. Check the file, looks the same because 1 is the default. Let's see what happens if we say 5. Reload. We can see that our stroke width has adjusted.
So, although that might be a bit elaborate, just writing your own Python sub for exporting an SVG, what you could do, of course, is just use the code that Niklas has written for us and just copy it into your file and then use that as an SVG exporter to Adobe Illustrator or any other vector drawing program. Thanks again to Niklas for agreeing to collaborate with us and do this tutorial. If you want to check out more of his stuff, just go to niklasrosenstein.com. He's got an amazing assortment of tools for anything CG, be it Houdini, Cinema 4D, or anything Python in general. As always, we'd like to thank our patrons, especially Mohammed Alabri, Mikhail Ivanov, Rob Bryan Jr., Rafik Anadol, Chris Hebert, Nick, John Coons, and Joseph Howerton. Thanks, guys. So, until next time, it's cheers and goodbye.